So today we will clear up one issue that I promised I'll talk about, which is to justify why we could use the electron mass in our calculations in the hydrogen atom problem. And after we are done with this, we'll switch gears and move on to a new subject, and the subject of perturbation theory. Okay, so today I want to sort of briefly tell you about the two-body problem in quantum mechanics. Okay. So remember that the hydrogen atom, or any atom that you can think of, there is actually two components, not just the electron. There is a central nucleus, right, comprising of protons, however number of protons there is in the atom, and electrons around it. Okay, so there is a nucleus and a electron. So let us consider a very simplified picture where we have the hydrogen atom, which is composed of one proton and one electron. So there is actually two different actors in this scenario, and we have to understand the dynamics of both these guys, right? So if I write down the momentum operator corresponding to the electron as Pe, okay, and the momentum operator corresponding to the nucleon as Pn, and denote the mass of the electron by Me and the mass of this guy by Mn, then I can write down a Hamiltonian for this interaction. The Hamiltonian for this interaction is basically Pe squared over 2Me plus Pn squared over 2Mn plus a potential energy term, but you should understand that the potential energy term only depends on the absolute distance between the electron and the nucleon. So this is a function of Xe minus Xn. So I'll write it this way: Xe minus Xn. These are all operators, obviously. Okay. So this fact is important, that it is only proportional to the absolute magnitude of the distance between these two guys. Okay. Since the potential only depends on the absolute magnitude, we can gain some simplification here. This is something you do routinely in classical mechanics, and we will do the exact same thing here in quantum mechanics. Also, we will introduce a change of coordinates. So instead of looking at the coordinates of the electron and the coordinate of the nucleon, let me change to what is called the center of mass coordinate. So the center of mass coordinate, X, is defined as MEXE plus MNXN divided by the total mass, which is Me plus Mn, and the relative coordinate X, which I'll call X, which is Xe minus Xn. Now, why do you want to do that? Well, the hope is that this simplifies the problem, because the potential is a function of the difference between the electron and the nucleon coordinates, right? So since the potential is only a function of the difference between electron and nucleon coordinates, if I introduce a new set of coordinates which explicitly depends only on the difference between the electron and nucleon coordinates, then the potential would only be a function of little x and not a function of capital X. Okay, and this will simplify the problem, as you will see in just a second. So correspondingly, I can introduce a relative momentum and a total momentum. The total momentum, the total momentum P is obviously the electron momentum plus the nucleon momentum, and the relative momentum little p is equal to mu times Pe over Me minus Pn over Mn. Okay, where mu is called the reduced mass, which is defined as MEMN divided by Me plus Me. Okay, these are all simplifications that you must be used to from your usual classical mechanics problems. And we can adopt the same manipulations in quantum mechanics also. So instead of writing the Hamiltonian as a function of Pe, Me xe and Pn, Mn, and Xn, we are now going to write the Hamiltonian as a function of little p, little x, and mu, and capital P, capital X, and the total mass M. Okay, so basically this is just a change of coordinates, but except that in quantum mechanics, you should remember that PE is an operator which is minus IH bar del E. Okay, which means Px is also an operator which is minus IH bar del X. Pn is an operator which is minus IH bar del M, and capital P is also an operator which is, okay, so in other words, this is minus IH bar dd capital X, dd capital Y, and dd capital Z. Right? Those are the components of this particular operator. So you can do this simple calculation, and you can write the Hamiltonian in terms of little p, capital P, and the Hamiltonian, the exact same Hamiltonian written in the new variables would look like little p square over 2 mu plus capital P square over 2 times the total mass plus V, which is only a function of little x and not capital X. Okay, so now, so also the commutation relations between these guys is xi, little pj is IH bar delta ij, capital Xi, capital Pj is also IH bar delta ij, but little xi and capital Pj and capital Xi and little pj, commute, right? Because they act on different particles. Okay, so you should remember what the commutation relation is. So the Hamiltonian, which is written in terms of the momentum of the electron and the momentum of the nucleus times the potential energy term, which depends on the absolute distance between them, can be recast into a Hamiltonian, which is little p square, capital P square, and V, which is a function of only little x and not capital X. Okay, so which means, remember that the solution of this guy, H, so suppose I write H in terms of coordinate space, H, which will be a function of little x and capital X, should be equal to E psi little x capital X. This is the time independent Schrodinger equation. But if I substitute this over here and then work this out, you would see that since the potential does not depend on capital X at all, as far as capital X is concerned, the motion is basically just a free motion. In other words, I can do a change, I can do a separable solution. I can try a separable solution of the form, this is equal to some psi of x times some capital F of x, right? And if I substitute this on sorts over here, I would simply get that capital F of x is some e to the I p dot x over h. Okay, this is very easy to prove. I encourage you to simply substitute it and show this. Basically, you will get capital P squared over 2m times f is just a constant times f. Okay, so now that we have gotten this, we can now claim that our solution, which is xx, the only non-trivial part of the solution is basically the solution for little x. Okay, and the solution for little x can be gotten by solving the Schrodinger equation minus h bar square over 2 mu del little x square psi of x plus v of x psi of x equals e psi of x. Okay, where little v of x is of course for the Coulomb potential is just minus e square over r, and this mu, which is me mn over me plus mn, for this particular problem is very close to the electron mass, because the mass of the nucleon is much larger than the mass of the electron. In this particular expression for the reduced mass, I can make the approximation that in the denominator here, I can neglect the mass of the electron, and this mu would simply be me mn by mn, which is just me. Okay, so this is why when you solve the Schrodinger equation, you write down the dynamics for only the electron, because the motion of the nucleon is basically captured by the e to the ipx. It is just the motion of the center of mass in your classical mechanics. Okay, so the non-trivial part of the dynamics is encoded in the Schrodinger equation for the motion of the electron, which is given by this equation. Of course, we can now go ahead and write this in r, theta, and phi and do whatever we have done before and solve this equation. So this is how you treat two-body problems in quantum mechanics, okay, which is exactly same as how you would treat two-body problems in classical mechanics using the exact same change of coordinates and things like that. But you have to be a little careful in this because your p and x are operators and not just numbers. That is the only non-trivial addition to this aspect, okay. So with this done, I want to now switch gears and move to a new subject. And then this new subject in quantum mechanics falls under the general umbrella of what are called approximation methods. Okay. So up till this point in our quantum mechanics course, we have always been able to solve the Schrodinger equation for any given potential. Okay, but we should keep in mind that most of these situations, except for the hydrogen atom and the harmonic oscillator potentials that we solved, most of these other cases are rather artificial, in the sense that if you encounter a real world situation, real world situations will not be a very clean potential bump like that, or a potential well, or things of that sort. Of course, as I've told you, we can approximate many of the real world potentials by these artificial potentials, and they give you good answers to leading order. But in general, problems are hard. Problems are hard to solve because if you have a potential, for example, even if you think of a one-dimensional problem in quantum mechanics, v of x, I can think of a v of x that is some, alpha x square plus beta x cubed. Okay. Now the alpha x square part, you know how to solve it, is just your simple harmonic oscillator. But if I add a beta x cubed there, then the problem becomes much more complicated, right? So I cannot use A and A dagger anymore because the Hamiltonian will not be separable anymore. So I'll have to solve a very complicated looking differential equation, right? The Schrodinger equation, which is just this that I've written here, the v of x here is alpha x squared plus beta x cubed, and this is in general a very complicated looking differential equation. So this is true in general in physics. Like if you have any general potential, it is very difficult usually to get analytical results exactly, okay? But it so happens that in many cases, many of these potentials have some nice properties. What are the nice properties? The part that is complicated, for example, if it so happens, the part that makes the potential complicated is also something which is rather weak compared to the other stuff. So for example, if I look at this potential and I have an alpha x squared plus beta x cubed, but I know that this coefficient beta is very, very, very small compared to alpha. Okay, then I can sort of think of this potential as mostly just a simple harmonic potential masking this beta x cubed plus some small corrections to the simple harmonic oscillator problem. Okay, so this is an introduction to what are called approximation methods in quantum mechanics, and there is very many kinds of approximation methods that one employs. Perturbation theory is one example, variation method principle is another example, WKB approximation is another example. And even within perturbation theory, you have a time-dependent and time-independent perturbation theory. So there is very many classes of approximation methods that one employs in quantum mechanics to study the effect of potentials that are otherwise difficult to solve exactly. Okay, so today we will begin our introduction to one of these approximation methods. And what I'll be talking about today is what is called the time independent perturbation theory. Time independent here means that the potential is time independent. I'm not going to consider time dependent potentials. I will consider time dependent potentials in the next semester when we do quantum mechanics too. For now, we will look at time independent problems. Okay. So that is the time independent part. So what is the perturbation theory part? Well, so the general philosophy of this is as follows. Suppose you are solving some Hamiltonian. Let us call this Hamiltonian H with a suffix of 0. Okay. So let us say that this is some Hamiltonian that you know how to solve exactly. Solve exactly. And you know what the eigen energies are. We will call the eigen energies E and 0. And we will call the eigenkets N0. Okay, in other words, for this particular Hamiltonian H0, I know exactly what the solution of the time independent Schrodinger equation is. Okay, H0 is of course a Hermitian operator, which means that my N0s form a complete basis. Right? So in other words, N0, M0 is delta Nm, and there is a completeness relation between the kits. Okay, what does this mean? This means that in the space of the eigenkets N0, I can expand any vector I want. Okay, any vector alpha can be expressed as a linear combination of the N0s. So I know everything about this Hamiltonian. For example, this Hamiltonian could be the simple harmonic oscillator Hamiltonian. You know exactly what the eigenkets are. You know exactly what the eigenenergies are. Or it could be the hydrogen atom Hamiltonian. You know exactly how to solve it. We just solved it last class, right? So there are examples of Hamiltonians which can be solved exactly. But suppose to this Hamiltonian, I add something else. I construct a new Hamiltonian, which is this H0 plus some lambda times some tilde H. Okay, and I will call this part, I say perturbation. Okay, what is a perturbation? I'm simply saying that to the Hamiltonian H0 that you know how to solve exactly, I'm adding a small piece. Okay, so for example, H0 could be p square over 2m plus 1/2 kx square, and H tilde could be some beta x cubed, something like this. I'm adding a term, but I'm also claiming that this term is very small compared to the term H0. In other words, H0 is called the unperturbed Hamiltonian, and H tilde is called a perturbation. Okay. Now, what is the lambda? The lambda is simply a bookkeeping device. Okay. So I'll tell you what the use of lambda in just a second. Okay. Now the point is, if I want to solve for the eigenkets and eigenenergies of capital H exactly, it would be very difficult. For example, as you can clearly see, if I add a beta x cubed term to the harmonic oscillator, in general, for any value of beta, this is very difficult to solve. But if I assume that my beta is a very small parameter, and that for all values, beta x cubed in some sense is very small compared to the effects of the unperturbed Hamiltonian H0, then I can develop an approximation technique, and I can understand what the corrections to the energy levels are. So the philosophy here is that I know what the unperturbed eigenkets are. Unperturbed kets, these are the n zeros, and I know the unperturbed energies, these are the en zeros. Okay. Now, with the entire Hamiltonian H, there will be some correction to the unperturbed kets and unperturbed energies. So let us call the eigenkets of the entire Hamiltonian as n, and let's call the eigenenergies as En. Okay. Now, basically the point here is that I can understand the solution to the full problem, which is basically determining En and n, as some kind of a series with respect to the unperturbed kets and unperturbed energies. In other words, I can understand En as mostly just being the unperturbed energy En0 plus corrections. And I can understand N as mostly the unperturbed ket plus corrections. Okay. So time independent perturbation theory is a technique that tells you how to compute these corrections. Okay. Now, before we develop the formalism of time independent perturbation theory, and before I tell you how to calculate these corrections order by order in the small parameter lambda, let us actually do an example. Okay. But before we do an example, are there any questions about the basic setup of this problem?
Hello, sir.
Yes.
Why do we need the correction? I mean, we have the eigenkit and the eigenvalue. They has zero uncertainty. So why do we need corrections?
No, I only know the eigenkets and eigen energies of H0. I do not know the eigenkets and eigenenergies of capital H. See, remember there is two parts to the problem. Remember that my total Hamiltonian is written as H0 plus a correction, right? Now the correction term really screws things up for me. It makes my life difficult. So I give an example here. Like if I add a beta x cubed to the simple harmonic oscillator, I cannot solve for it exactly. It is very difficult in general to solve for these differential equations, right? So what I'm going to claim is that, look, if this beta x cubed were not there, I know exactly what the eigenfunctions of the simple harmonic oscillator are. I know what the energies are. It is just n plus 1/2 h bar omega. So I will pretend that this beta x cubed term is very small, okay, compared to the unperturbed Hamiltonian H0. And then I will develop the solution for the full problem, the eigenkets and eigenenergies of capital H, as mostly being comprised of the eigenenergies and eigenkets of the unperturbed Hamiltonian plus some small corrections. Do you understand?
Yes, sir. So you are saying that we have another different problem which we are trying to approximate into the simple harmonic oscillator problem, right?
Not just simple, that is just in general, some Hamiltonians. See, let us say that you have some Hamiltonian H0 about which you know everything. Okay. Now somebody comes along and says, okay, everybody knows how to solve this problem, solve this problem. And he gives you some other Hamiltonian. Okay. Now this problem in general can be very difficult to solve. See, this is what we want to solve, right? Agreed?
Yes, sir. Yes, sir.
This problem can be very difficult to solve in general. I don't know how to solve it in general, right? So what I'm claiming is that if this second piece that I'm adding here, this guy, if this is small compared to the first piece, then I can write down the solution. So if this were very close to 0, I know the solution, right? It is just n0 and en0. So basically I'm claiming that if you modify my Hamiltonian slightly, then my energies should be modified slightly and my eigenkets should also be modified slightly. Make sense?
Yes, sir.
So I'm going to calculate this modification. Okay, that is what I want to do. Make sense?
Yes, sir.
Okay. So before we do it, so again, I told you that in general, these are difficult to solve, but let us get a flavor of what this means in the context of a problem that we know how to solve. Okay. So let us take a very simple example. I'll take the example of a two-state system. Okay. So let us say that I have a Hamiltonian that I know exactly how to solve. Okay, which means I can write this Hamiltonian in the basis. I'll call this 1, 0 and 2, 0. Okay, and I have a Hamiltonian which is H0 equals some E1 plus E2. Okay, what does this mean? This means that this Hamiltonian, if I write it as a matrix, this Hamiltonian in the 1, 0, 2, 0 basis has the form E1, 0, 0, E2. It doesn't have any off-diagonal elements. Okay, and of course, the eigenvalues of this Hamiltonian are E1 and E2. So eigenvalue corresponding to E1 has eigenket 1, 0, and eigenvalue E2 corresponds to the ket 2, 0. So I know everything about this Hamiltonian. I know the eigenkets, which is 1, 0 and 2, 0, and I know the eigenvalues, which are E1 and E2. Okay. Now to this Hamiltonian, about which I know everything as far as solving the time-independent Schrodinger equation is concerned, I will add a perturbation. How will I add the perturbation? So I will claim that, look, I'm going to add some amount of off-diagonal elements in this Hamiltonian. So I'm going to add the off-diagonal elements in this fashion. So I'm going to change this H0 to some H. Okay. And what is this H? This H I will write as, I am not going to do anything to the unperturbed Hamiltonian. That is still going to be there. Okay. But I'm going to write down a V12 and a V21. Okay. So in the eigenbasis 1020 or in the basis 1020, this Hamiltonian has the form, a matrix form, which is equal to E1, E2, V12, V21. Okay. Now Hamiltonian has to be Hermitian. I should always ensure that this is Hermitian, which means that I should always ensure that V12 is equal to V21 star. Okay. Now, since this is just an example, I will simply take the V to be a real quantity, and I will simply write my Hamiltonian. So I'll write this down explicitly. Let V12 be real. I don't want to introduce any phases or things like that. So I will write this Hamiltonian in a simplified form as E1, V, V, E2. Okay, and I can think of this Hamiltonian as a sum of two Hamiltonians Okay. Now I will also introduce a parameter lambda here. Okay. So lambda. I don't need to introduce the parameter lambda, but I'm going to introduce it just for just as a bookkeeping device, as you will see in just a second. Okay. The use of the parameter lambda. Lambda is some small parameter which has a value between 0 and 1, right? So I can use lambda as a tuning parameter. That is why this is very useful. So instead of claiming that B is small compared to E1 or E2, I will claim that lambda is a very, very small number. If lambda is 0, then I have a purely unperturbed Hamiltonian. And if lambda is 1, I have a perturbed Hamiltonian. Okay, so it is kind of a tuning parameter. Now, I don't need to show you how to solve for the eigenvalues and eigenvectors of this matrix. You know how to solve this exactly. I don't need perturbation theory for it. But I simply want to motivate the form of corrections. That is why I'm doing it. In particular, the form of the corrections for the eigenenergies. So let us diagonalize this Hamiltonian. You know how to solve for the eigenvalues for this Hamiltonian H1, which is equal to E1 lambda V E2. Right? How do you solve for it? You simply look for the characteristic equation. Oh, there is too many lambdas here. Right? So let's call the eigenvalues as omega. Okay, and then you can solve for the corrected values. Oh, I'm sorry, I actually made a mistake here. I'm going to write E1 0, E2 0 here because it's the unperturbed energies. Okay, so let me keep track of what are the unperturbed energies. Sorry. Okay. So I want to calculate the eigenvectors and eigenvalues and eigenvectors of this Hamiltonian. So let me just calculate the eigenvalues. The eigenvalues you can calculate very easily, and you can show that the eigenvalues of this, which I'm calling E1 or E2, is equal to, if I'm right, this is equal to let's see, E1 0 plus E2 0 over 2. This will be a quadratic equation, as you can easily guess. So this will be the new energies or new eigenvalues of this Hamiltonian. Of course, we don't need any approximation. These are the exact eigenvalues of this Hamiltonian. But now let us pretend that now this lambda V is a very small quantity compared to the difference E1 minus E2. So, okay, suppose if lambda V is very, very small compared to E1 0 minus E2 0. Okay, then I can use the binomial theorem and expand these guys. So E1 2 can be written as E1 0 plus E2 0 over 2 plus minus E1 0 minus E2 0 over 2 and square root of 1 plus, I should have, what should I have? 4 lambda square V square divided by, like this, right? Now, if lambda is lambda times V is very, very small compared to the unperturbed energies, E1 0 or T0, or even the difference between the two, then I can develop a power series. So 1 plus epsilon, as you know, is approximately 1 plus epsilon over 2 minus epsilon square over 8 plus blah, 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 16 and over. So if I introduce this to first order, this is approximately equal to just 1 plus epsilon over 2, right? The question is, how many orders should I keep? So if I expand the square root, 1 plus 4 lambda square V square over E1 minus E2 whole square, I can, depending on how much accuracy I want in the problem, I can retain terms. I can just throw it away completely if I don't want any perturbation, which if you put lambda equal to 0 in this equation, you can clearly verify that your energies would still be E1 0 and E2 0. Okay, if lambda equal to 0. So if lambda is not equal to 0, then you should develop some power series for the correction terms. So what is the first correction here? The first correction here would be just the epsilon over 2 piece. So what will this be? E1 2 would be equal to plus minus 1 plus 2 lambda square V square over E1 0 minus E2 0 square. Okay, which means E1 is equal to, I can write this as E1 0, first order, the unperturbed energy, plus lambda square V square E1 0 minus E2 0. And E2 can be written, of course there is other terms also. E2 can be written as the unperturbed energy E2 0 plus again the same. This is a very simple problem which I was able to solve exactly like this. Now let us take a moment and understand what this is telling us. This is telling us that if I solve for the exact energies for this problem, I'm lucky I can solve for the exact energies. But if I don't want the exact energies and I simply want to write down an approximation technique by expanding the square root, then my first correction to the energy E1 is of order lambda square. Okay. Now notice that when I wrote down the Hamiltonian, my Hamiltonian had a correction proportional to lambda. Okay, my H, this was equal to H0 plus lambda times H tilde. So my H had a correction proportional to lambda. So in general, I can expect that the corrections to the eigenvalues would have a term that goes like lambda, a term that goes like lambda squared, a term that goes like lambda cubed, and so on and so forth, if I expand this square root in general. Similarly, the correction to the eigenkets can also have a term proportional to lambda, a term proportional to lambda squared, a term proportional to lambda cubed, and so on and so forth. But in this particular problem, it so happens that the eigenenergies do not have any corrections to order lambda. Okay, and they only have a correction to order lambda squared. This can also happen in some problems. Okay. Similarly, they will not have any correction to order lambda cubed. They will only have even corrections, lambda to the fourth, and so on and so forth. Okay. So a correction to order lambda is called a first order correction. A correction to order lambda square is called a second order correction. A correction to the higher order is a lambda cube term would be a third order correction, and so on and so forth. But for all practical purposes in perturbation theory, second order corrections are the most that you would actually do. Okay, you would never do more than that, because there is always an underlying fundamental assumption here that the corrections are rather weak. Whatever is perturbing the Hamiltonian H0 is actually a weak term. Okay, remember that I don't have to use lambda at all here. I can simply use H tilde and pretend that it is weak. But lambda is just a bookkeeping device, and the power of lambda tells you which order of perturbation that you're correspondingly looking at. Okay, so this is the philosophy behind perturbation theory. Perturbation. So again, I can also solve for the exact eigenkets for this problem, and you would actually guess that it will be 1, 0 plus corrections. And similarly for the eigenket 2, and so on and so forth. Okay, so perturbation theory is a formal procedure for telling you how to compute these corrections given the perturbation. Okay, the formalism of perturbation theory, which we will now go to, tells you exactly how to solve for these corrections to the eigenenergies and eigenkets. Remember that nature is not always very kind. You cannot always get problems that you know exactly, and then you can simply expand the square root. This is an artificial example where we started with a problem that we knew exactly how to solve. But in most cases, we would not know how to solve for the exact energies and exact eigenkets. If you knew how to solve for it, then we would not even need perturbation theory. The whole point is we don't know how to solve for the exact energies and exact eigenkets, but we still want to write the exact energies and exact eigenkets as a series in the small parameter lambda. Okay, so this is the statement of the problem. The problem is that you know everything about the unperturbed Hamiltonian. You know that n zeros form a complete basis. You know exactly what the en zeros are, but you don't know anything about the perturbed Hamiltonian. You know that they also have to solve the time-independent Schrodinger equation. But you don't know, we need to calculate, we need to compute En and N. We don't know what they are. Okay. So there is a question, how did you write E12 expression? Did you assume it? No, I did not assume it. you can do it also. You simply diagonalize this Hamiltonian that I've written here. Okay. So E1, 2 are basically the omega 1 and omega 2 in this example. Omega 1 I'm calling E1 and omega 2 I'm calling E2. These are the two eigenvalues for this particular 2 by 2 matrix. Okay. This is very easy to solve.
Hello, sir.
Yes.
Sir, all the correction term you added in the Hamiltonian, in the off diagonal element, why don't you add one of the term in the diagonal element?
No. So if I add something in the diagonal element, that becomes part of the unperturbed Hamiltonian, right? So the whole point is I know exactly everything about the unperturbed Hamiltonian. So if I do add something in the diagonal part, I will treat it as part of the unperturbed Hamiltonian anyway, which I know how to solve. So here's what you're hinting at, right? So suppose if instead of writing the Hamiltonian H0 as, let us say, E10 lambda V1 lambda V E20, why don't I write H as E10 plus lambda W lambda V E20 plus lambda W? That is the question, right?
Yes, sir.
But I can always treat this as E10 plus lambda W E20 plus lambda W plus 0 lambda V 0, right?
Yes, sir.
This is a diagonal Hamiltonian. This has an eigenenergies E10 plus lambda W, E20 plus lambda W.
But sir, if I don't add any term in the off diagonal element, I add all the term in the diagonal element, won't be this much more easier?
Of course, it will be much more easier, but that is not what you get usually in nature, right?
Yes.
So then you are not doing anything.
Yeah, exactly. I'm not doing anything actually.
So okay, is it okay?
Yes, sir. Okay.
All right. So now we need to compute En and N, and I'm going to assume that just as we found for this problem that we can always write E1 and E2 as a power series in the small parameter lambda, I can do this in general. So I will write down my N as the unperturbed get N0 plus some small correction to the proportional to lambda, which I will call N1, plus a correction proportional to lambda square, plus a correction proportional to lambda cubed, and so on and so forth. Similarly, I'll also assume that I can write the exact energies En as the unperturbed energies En0 plus a small correction plus a lambda square correction plus so on and so forth. Okay. Remember that you should not read this as En square. This is not En square. This simply means that this is a second order correction to energy. Okay. So En1 is the first order correction, and N1 is also the first order correction to the eigenkette. Okay, N1 means it is the first order correction to the nth eigenkette. So in the example here, I can write 1 as the unperturbed ket plus lambda square times the first order correction plus so on and so forth. In this case, there won't be any lambda correction, there'll be a lambda square correction. And similarly for 2. Okay, so that is what I'm writing in general. So what I will do is I'll substitute this on sorts in the full Schrodinger equation, which I've written here, and then I will just compare them term by term. So what do I mean? I mean that if I write this Hamiltonian again, which is H0 plus lambda times the perturbation acting on N0 plus lambda N1 plus lambda square N2 plus so on and so forth equals En0 plus lambda En1 plus lambda square En2 so on and so forth times again N0 plus lambda N1 plus blah blah blah. Okay. So how can a term like how can an equation like this be equal? An equation like this can be equal if every power of lambda on the left hand side of this equation is equal to the same powers of lambda on the right hand side of this equation. That is the only way in which this equation can hold true. So let us write down the left hand side. Let us write down all terms proportional to lambda to the power 0. There is only one term, which is h0 times n0 on the left hand side. So let us collect all terms proportional to lambda on the left hand side. Well, there are two terms. H0 acting on this is proportional to lambda, and this guy acting on this is also proportional to lambda. So there is two such terms. So I can write H0 acting on N1 plus H tilde acting on N0. Okay, this, I'm so sorry, I'll write it in a new page because I don't have enough space here. So the first order correction, the 0th order, is basically H0 acting on N0, and this is equal to, on the right hand side, En0 N0. This is the lambda to the 0th term. Of course, there is nothing strange about this equation. These are the eigenkets and eigenenergies of the unperturbed Hamiltonian, and we know how to solve this problem exactly. So the first non-trivial correction is the first order correction. First order correction is lambda H0 acting on N1 plus H tilde acting on N0 equals lambda. The first order correction on the right hand side is En0 acting on N1 plus En1 acting on N0. Okay. So this is why I told you lambda is a bookkeeping device. Now I can throw away the lambda completely. Okay. And I can write this equation as H0 acting on the first order correction to the nth eigenket plus the perturbation acting on the unperturbed nth eigenket equals En0 times the first order correction to the nth eigenket plus the first order correction to the energy of the nth eigenket times the unperturbed eigenket N0. Okay, so this is the equation that we will be fundamentally interested in. Now notice that this equation mixes up both the corrections to the energy and the corrections to the eigenket, but with some very simple manipulations, we can extract formulas for the corrections to the eigenenergies and the corrections to the eigenkets separately. How we will do it, I'll demonstrate in the next lecture. For now, we will stop here. And hopefully the goal here was to develop a formalism, not completely at least, but explain, more importantly, explain the philosophy of perturbation theory. And please make sure you understand that correctly. If there is any questions about the second part of the lecture, where we develop this series solution, we can also revisit this in the next lecture if you have any questions. Okay. So for today, I will stop here and we will continue in the next lecture.